Hello, everybody. Welcome from my side to this FLEUR hands-on online workshop at the Forschungszentrum Jülich here in Germany. My name is Stefan Blügel, and I'm heading the Department Quantum Theory of Materials, which is member of the Peter Grünberg Institute and the Institute for Advanced Simulation, and feels responsible also for the development of this open source community called FLEUR. I'm convinced that many of you have already experienced with density function theory in one form or the other. Maybe some of you have done already density function theory calculations. Some of you may be super expert. You may come from fields like physics, chemistry, biology, mineralogy, geology, nanoscience, very wide diversity of fields. Maybe you have heard already density function theory lecture in your university or at your course. And the mission of this particular talk is basically to collect, to bring you all on the same footing, and getting the right nomenclature and getting you tuned to this particular workshop. Oops. All of you probably are familiar with the Schrödinger equation, which is a wave function representation, wave function equation for quantum mechanics. Here written in for the stationary state, you see the kinetic energy, the electrons interacting with the potential. The solution is a wave function. The wave function gives you the square of the wave function gives you the probability of the electron distribution. The solution is a consequence of an eigenvalue problem with the proper boundary condition, which gives you also the energy of a particular state. That is the quantum, the Schrödinger equation is basically a theory which we would call from first principles, or in Latin ab initio. As it does not make any assumptions that such as empirical models or parameter fitting. It starts directly at the level of the established science. I'm convinced that many of you have solved this Schrödinger equation, at least for one particle, maybe in one dimension or in 3 dimensions. Here, for example, I show you the example for the solution of the hydrogen problem, where you see the square of the wave function gives you the probability distribution, for example, for the S state, for the P state. The nice thing about this quantum mechanics and the Schrödinger equation, it is easily extendable for many electrons. You see here the kinetic energy of the ions. You see here the kinetic energy of the electrons. You see here the interaction of the electrons with the ion. The electrons are the position of the electrons are described by small r, position of the ions by the capital R. You see here the electron-electron interaction, which is enriching our life or make our life complicated. And you see here the repulsive Coulomb interaction of the ions. Also, the electron-electron interaction is repulsive. We see this in the positive sign. The interaction of the electron with the nuclei is negative. You see this here with the negative sign. The way I've written down the equation is in atomic units. So you have units of Bohr radii, and the energy is given Hartree energy. And with this formulation, you see 2 quantities I cannot scale away. One is the ratio of the electron mass to the mass of the ions, and one is the nuclear number. I guess in first approximation, I remember that the mass of the electrons is small and the mass of the ions are large. Therefore, in zero order kinetic approximation, I can ignore the kinetic energy of the ions. And as soon as I ignore this, I know that the position of the atom is a constant of motion. And in particular, the distances between atoms are constant of motion, and therefore we have here actually, this guarantees actually the spatial structure of the matter, such as the configuration of the molecule or the position of the atoms in the crystalline solid. So basically, ion positions are fixed, or better, the difference between ion atoms are fixed. We can do a perturbation theory about the adiabatic approximation or the Born-Oppenheimer approximation. It is very crazy that, or rather bizarre, that the entire matter, organic, inorganic, is basically controlled by one number, which is the nuclear number. The dependence of all these properties on the nuclear number is rather bizarre, but we know the periodic table, where we have some periodicity in the different in the periodic table. And this periodicity we transfer also to the solid. The nice thing about the quantum theory, we can also give the exact solution of this problem, which is the many-body wave function. And the many-body wave function depends on the position of the electrons and parametric on the position of the stationary atoms. For example, for the cobalt, not for the cobalt, for the carbon dioxide molecule, we have for the oxygen, we have 8 electrons, for carbon 6 electrons, for oxygen 8 electrons, makes in total 22 electrons. We have 3 coordinates, makes in total 66 degrees of freedom. So we have to represent the wave function of this CO2 molecule in 66 dimensions. And if you plan to resolve the wave function by 100 grid points in each dimension, then we have 100 to the 66 power dimension grid points. And for sure, this is not a wave function which we can store. This problem has been recognized or realized already in the 30s by, for example, Dirac. And he wrote in his paper, "In general theory of quantum mechanics is now almost complete. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole chemistry are thus completely known. Exact application of these laws leads to equations much too complicated to be soluble. And we need approximate practical methods without too much computation." So this was the 30s, and we are still working on this. One example where you can do one example of an approximate solution is using a variational ansatz for the unknown wave functions. That means you take the Rayleigh-Ritz variational principle, and you basically take a wave function, which is maybe a good ansatz due to a strong physical intuition. And then you take this strong physical intuition and you construct a wave function which is flexible, parameter-wise, curvature-wise, functional-wise. And then you make an ansatz for this wave function and minimize this ansatz, these parameters or these expressions with respect to the wave function, with respect to these parameters. And you find the optimal, the best possible wave function in this set which is allowed. And if the wave function matches exactly the ground state wave function, we find the ground state energy. Otherwise, we stay above the ground state energy. And we know, of course, that each wave function on the Hamiltonian depends on these configurations of the atoms, but we do not go into it in detail today. We keep it in mind. A very famous ansatz for a wave function is the Sliter determinant of independent single particle wave functions, because it includes automatically the antisymmetric nature of the many-body wave function. So the Sliter determinant is expressed by single particle wave functions, where all the electrons can be in all possible states. And this n factorial combinations is expressed by products, which we can be elegantly write in terms of this Sliter determinant. And if our Hamiltonian does not depend on the spin explicitly, we can write the wave function, a single particle wave function, which depends on position coordinates and the spin coordinate is a product of a spin-independent wave function and a spinor wave function. And with this, I come to the Hartree-Fock approximation, because in the Hartree-Fock approximation, you look now for the best possible Slater determinant in the sense of a single particle wave function under constraint that your wave functions, single particle wave functions are normalized for all occupied states. That means you minimize now this expectation value for the Slater determinant with the Slater determinant as wave function with respect to the single particle wave functions under the constraint which you put in by Lagrange parameter that the wave function is normalized. And you minimize this energy not only according to one electron, but for example, in the case of the CO2 molecule, it would be 22 wave functions, 22 minimizations for 22 different states. And if you do that, you end up with the Hartree-Fock equation, which consists of the kinetic energy, the external potential, the Hartree potential, which is the potential of the electron in the repulsive potential of all the other electrons produced by the charge density distribution of the electrons. And to this charge density contribution belongs also the electrons we are looking at. And then the last term is given by the exchange correlation potential, which is given by the state-dependent pair potential. Obviously, the pair potential, pair density. The pair density is non-local, and it depends on the states which I'm looking at. So that means, and I can express this pair density through the wave function, and it looks pretty unwieldy. Obviously, the exchange potential is a potential that acts only on the state of the same spin. And this tells you also that this potential is spin dependent, and you can gain energy, and you see immediately maybe it has something to say with the emergence of magnetism in solids. And obviously, this pair potential is a little bit difficult to conceive, but what it does is it reminds you at the fermionic nature of the wave function. If you have an electron in state R or an electron in position R prime, and they both have the same state, if these electrons approach each other, the probability of meeting is very low. It's basically zero. This we call the exchange hole. And this exchange hole guarantees now that the Hartree-Fock theory is actually self-interaction free, because it cancels exactly for this particular case that electrons are in the same state and at the same position. It cancels actually against the density. Now, you can immediately see how things are continuing. You have the first Slater determinant. Now you can have the second Slater determinant, the 10th Slater determinant. You can have 100th Slater determinants, and you have millions of Slater determinants. The more wave functions you have, the more wave functions you include, just the more precise your results will become. And this goes basically in the direction of quantum chemistry. But parallel to the Hartree theory, which is the Hartree-Fock theory, which are a wave function-based theory, there's also at the same time a second theory, which is completely different, which does not dwell on the wave function, but on the density. But this is in the framework of the THOMAS-FERMI approximation, originating from nuclear physics. So you interpret the total energy as a functional of the density. So how do you describe the kinetic energy of electrons as part of the functional of the density. This you can do by taking the density-dependent kinetic energy of the homogeneous electron gas. So if you have a homogeneous electron gas, your eigenstates will be a wave function. The wave function will be a plane wave. You have the number of planes you have. You can occupy all your plane waves up to the highest occupied states with the Fermi wave vector. This gives you then finally the kinetic energy. The Fermi wave vector is related to the density of the homogeneous electron gas. And now you go one step further. You say, if my density is slowly varying, this is the local density approximation. This is you do the local density approximation to the kinetic energy and say locally what I have derived here, I take locally for each position R if the density is slowly varying. And then you get, so to say, a density distribution, which depends on this, on the power 5/3. And this you can add now to the interaction of the density with the external potential and with the Hartree energy. And so you have a density functional which you can minimize with respect to this density, and you get the density and differential equation for the density distribution, which you can then solve. Here's an example. I've solved it for this argon atom, and you see here the density distribution in the Hartree approximation. You see of a kind of a shell structure, which is totally lost in the case of Thomas-Fermi theory. In the Thomas-Fermi theory, you get something like mean field. You get a much too long tail. And the reason why you lost this shell structure is because the kinetic energy, which is a large number in the atoms, is not well reproduced by this local density approximation to the kinetic energy. But it is, so to say, a completely parallel direction in solid-state physics to the wave function theory. And then in 1964, with the paper of HOHENBERG-KOHN, they established now the density as the basic variable in quantum mechanics. Known is that the external potential and the number of electrons determine uniquely the charge density n. But what the theorem 1 of HOHENBERG-KOHN says, you can invert that statement. For a given external potential, the ground state properties of a system are uniquely determined by the electron density alone, and they are functionals of the density. There's a second theorem which says that the exact ground state density minimizes the energy functional. Both of these can be proven. So what you know is you have a potential, and if you solve the Schrödinger equation, you get a wave function to this given potential. And if you take the square of this wave function and you sum up over all occupied state, you get basically the density. So if you think about it, you have a mapping of the potential to the wave function and from the wave function to the density, or you can construct a mapping G, which maps surjectively the potential onto the density. And what HOHENBERG-KOHN theorem says, as G is basically invertible. So how does the proof work? It's by reducis and adsurdum. Nowadays there are nicer proofs available, for example, from Levy, but I'm not going into it. So basically I assume a contradiction. I'm saying that two different wave functions, psi and psi prime, map into the same density. So I'm assuming that I have a system with potential V, a system with potential V prime, which has the wave function psi prime and the energy E prime. And I have to show that different wave functions map onto different densities. but I make the assumption that they map to one density. So I'm looking for the energy as expectation value for system 1, the Hamiltonian 1 to the wave function 1. But if I replace in the system 1 the wave function by the wave function of system 2, then the energy cannot be optimal. According to Rayleigh-Ritz, it has a higher energy. And I can rewrite now the Hamiltonian H by the Hamiltonian adding the system 2 and subtracting the system 2. And since the difference between the system 1 and system 2 is only the difference in the potential 1 and 2, I can now write the total energy of the system 1, which has the energy E, in terms of the energy of the system E prime, and the difference between the potential of the system 1 and 2, and the density 2. And I can do exactly the same story for the second system, which is then given by the energy E, the density N, and the difference between the potential of system 2 and 1. See, this is exactly the opposite sign as this one. And if I assume now that I map to the same density, which I assume here, then I can replace this density and this density by the same density. I can add 1 and 2 and see that the energy E, the energy of system 1 and system 2 is smaller than the energy of system 1 and the system 2. But this is a contradiction. So that means basically I can construct a universal functional. So I have the Hamiltonian, and the Hamiltonian has the kinetic energy, the interaction energy, electron-electron interaction, and the potential. And I can separate now the system-dependent external potential here. And what's remaining here is a functional. I call it the universal functional. And this universal functional is a functional which is universal. It is the same for all systems where the particles interact with each other by the Coulomb interaction W. According to theorem 2, the ground state density minimizes this functional. That means if I don't have a density, which is the ground state density, then the energy is higher than the ground state density. The proof is by construction, and the proof is rather simple. So maybe I don't want to spend much time on this proof. But basically what it is the density. If you know the density, you know the potential. And if you know the potential, you can solve the Schrödinger equation. So I have solved the, imagine I have solved the Schrödinger equation. And I have the wave function as function of the density. Then basically I have the energy with respect to the potential V. And if the density which I have is not the ground state density, then the wave function is not a true wave function. The wave function which I assume is the ground state density is not the wave function of the true ground state density. And therefore, the expectation value is higher than the ground state expectation value according to Rayleigh-Ritz. But if I have if I have the ground state density, then the ground state wave function to the ground state density is the correct wave function to this particular potential. And therefore, I reach exactly the ground state energy. So hence, the ground state energy and the ground state density can be obtained by an energy minimization process because you come always from above. So far, everything is very nice. What people often do not appreciate is how important it is to have an existence criterion. And this existence criterion was given to us by the HOHENBERG-KOHN theorem 1 and 2, because if you know there is a gold mine, you will find the gold mine. And here I show you how to find a gold mine. In the words of KOHN-SHAM means I'm leading you to KOHN-SHAM equations, which gives you a path to find give an explicit form of this functional, and this we call the KOHN-SHAM density functional theory. And this KOHN-SHAM density functional theory is the theory which 99% of all of us use when we mean density functional theory. So towards the practical scheme, imagine you have a system without interaction. If you have a system without interaction, your universal function depends only on the kinetic energy. And it turns out that the Slater determinant of non-interacting particles is exactly the solution to this functional form, to this universal functional. That means we have an exact solution of this functional in the limit of no interacting functionals. And this now we use this idea of this non-interaction functional. We use actually to establish a practical density functional. So we assume the central idea is we assume there exists a potential, and this potential will exist, which is the KOHN-SHAM potential. Is an effective potential in which the interacting electron behave as non-interacting electrons, but at the end having the same ground state density as the interacting system. So we write the energy functional, the energy as function of the density, as the energy of the kinetic energy of the non-interacting system, the density with the external system, the Hartree term, and something which we do not know correctly, but some rest, which contains the exchange interactions and the correction of the to the kinetic energy of the interacting system, which is correcting the energy to the non-interacting kinetic energy of the non-interacting system. So the variation of this energy with respect to the density gives now a term which is the kinetic energy variation and the variation to a external potential. And this external potential is the KOHN-SHAM potential. It is external because the electrons in this potential are non-interacting, which consists of the true external potential, the Hartree potential, and the exchange correlation potential, which is the variation of the exchange correlation energy with respect to the density. So our KOHN-SHAM equation, it consists of the kinetic energy, the KOHN-SHAM potential. The KOHN-SHAM potential depends on the density. That means we have to solve this problem self-consistently. So maybe we guess a KOHN-SHAM potential. From the KOHN-SHAM potential, we get the KOHN-SHAM orbitals and the KOHN-SHAM energy parameters. The square of this density gives us the square of the orbitals. KOHN-SHAM orbitals gives us the density. And this we can do then self-consistently. If we have the density, we can get the KOHN-SHAM potential and so on. So for this exchange correlation energy here on the exchange correlation potential here, we have to find approximations. And the great power of the density function theory is that relatively simple approximations are relatively powerful. I would like to give some small cautions. So the KOHN-SHAM orbitals as such has no physical meaning, except as a vehicle to construct the density. And this density is the exact density of the interacting system. In particular, the Slater type orbitals cannot be taken as an approximation to the many-body wave function. Likewise, these orbital energies, epsilon I, are actually Lagrange parameters and have no physical meaning. Of course, we will learn that to some extension they have a physical meaning. For example, in terms of Koopman's theorem, or in terms of other approximations. For the exchange correlation potential, we have kind of a for the exchange correlation approximation to the exchange correlation energy, we have kind of a Jacob's ladder in the sense of in the spirit of the fact that the more in a wave function based method, the more wave functions you have taken into account, most likely the energy becomes better. A priori, it is not so in density functional theory, but in general, what we see is we have different levels. For example, the density, functionals which depend on density, like a local density approximation, function which depends on the density and the gradient of the density, like the generalized gradient approximation. This function is now good enough, and since we have these functions, material science has adopted density functional theory. Of course, a natural step would be to take the second derivative, but it turns out that the second derivative to the density is often very unstable. So we take actually the kinetic energy density, and this leads to the meta GGAs. And a big breakthrough, which basically opened density functional theory for the field of chemistry, are the hybrid functionals, hybrid GGAs like V3-lib, because they guarantee kilocalorie per mole accuracy, which is needed, which is needed in chemistry and often called chemical accuracy. More you will learn about this in the lecture by Gustav Bielmeier on Thursday. So in summary, we have the KOHN-SHAM standard model, which is the computational approach in physics, chemistry, nanoscience, material science, biophysics, mineralogy, and geology. The total energy depends on the density, plus external parameters like the lattice constant, atom positions, magnetization directions. The variation of this energy with respect to the density gives us the KOHN-SHAM equations, which are secular equations. The solution of the secular equations are KOHN-SHAM orbitals and KOHN-SHAM energies. The meaning of these KOHN-SHAM orbitals are to construct the density, and with the density we can construct the KOHN-SHAM Hamiltonian, or the KOHN-SHAM equations, and therefore we have to solve this self-consistently. So we have mapped the quantum mechanical many-body problem to a nonlinear to a nonlinear equation, which is the KOHN-SHAM equation of single particle physics. The computational time scales roughly with cubic with the number of atoms, or cubic with the number of volumes, and cubic in the position. The theory is extremely successful. Last year, we have published 30,000 papers with the density functional theory worldwide. You see the distribution. Chemistry is large, material science is large. Chemistry uses typically hybrid functionals. Material science use typically gradient approximations. Nowadays, you have so many functionals that sometimes you need to worry which function I should use for which purpose. The large number of people is also a consequence that computing became cheaper and cheaper and cheaper. So the computing time, the speed of the computers increase exponentially with time. We are reaching now the pre-exascale and exascale performance. A computation that took 1 year in 1989 takes now 1 second in 2018. So we have a 30 million-fold increase in 1 generation of people. This enables a huge throughput capacity, which doubles every year, every 14 months. And so we're aiming today towards larger systems. More accuracy concerns electron correlations, longer dynamical simulations, atomistic domain, molecular dynamics or spin dynamics. I discussed in the lecture basically the static and dynamical properties related to DFT, relating DFT to the quantum space. There's a second big field, which is the excitations using GW or time-dependent density function theory. And there's also transport, where, for example, you can relate to the Kubo theory. And these provide very different computational challenges. We deal also with the large chemical phase space. So the combinatorics of the materials, minerals, and so on is so large that a human being alone cannot probably can study all this large phase space. So we move into autonomous high throughput computing plus data informatics. And as a last thing to keep in mind, this lecture, so we do KOHN-SHAM density functional theory. KOHN-SHAM means a useful way to write down the unknown function in terms of a non-interacting single electron wave functions. The density means everything can be expressed by electron densities. And density functional means there exists a one-to-one mapping between the energy or the potential and the density. So with this, I thank you very much and really enjoy the workshop.